All right, I'm starting OBS right now, so the whole lecture is going to be recorded. And since I moved things around a little bit over the weekend, I have to kind of re-find exactly where it's supposed to go. All right, so first, just to remind everybody that tomorrow, HP Enterprise is going to be here. Do you guys remember? Did I talk about that in this class? Okay. So that's tomorrow at noontime. So if you want to consider going to HP for an internship, you might want to go to the information meeting. Um, Apparently, there are some interests in having a continued dialogue between HP Enterprise and ARC, even after this particular meeting. So we'll see what comes out of all of this. Okay, so there might be more internship possibilities in addition to just of um, over here. Okay. So that's just a quick reminder of HP Enterprise for tomorrow. And then with that done, we are going to move on. So right now we are done with a lot of the topics. Your new lab is, let's see, so your new lab is this one here. It's absolute value. We are going to get started with this one today. And with this class, I think we haven't touched on this module. So we're going to start with this particular module. All right. The purpose of this module is to turn you guys into compilers. Okay, so each one of you will turn into a compiler so that if I give you C code, you will know how to translate that C code into assembly code. That's the objective of this particular module, at least as far as the control structure is concerned. So that's the main purpose. And in order to do that, the first thing we need to do is, there are several ways to refer to this. Code that is structured, not structured. Okay, so I call this the process flattening. So we'll go ahead and start with a very generic conditional statement in C, C++, or just about any programming language has if-else. So you have stuff, which is condition. Now, in other words, it is only the the condition itself can be really, really complex. Okay, it's just a placeholder. For block 1, block 2. Block 1 is the then branch, and block 2 is the else branch. Are we good so far? Okay. So, in fact, that block 2, which is after block 2. So what is at block 1? It's block 2, which is the else branch. So now the question is, does these two pieces of code do the same thing? Are they functionally equivalent? What do you think? Yeah. Okay. So are most people convinced that these two are in fact functionally the same? Good. Okay. But the second version, which is the one that has labels and go-tos, is probably not something you want to turn in CISP 400 or 430, or even in 360. Okay, because your professor would probably frown at this one and go like, "This is not good." Okay. Well, why do you think your professor may say this code here, is not good? Yep.
It's confusing. And you're jumping around in memory.
You're jumping around, yes. But that is actually what the first piece of code is doing anyway.
But you're specifying it yourself. So
Yes.
that's why it's bad. You can easily mess up. And
Right.
Easily.
Yep. So the way you can mess up is to use the wrong name of the labels, right? If you, instead of going to go to L2 here, if you mistype it as L1, the compiler won't catch that. It won't catch the fact that you're supposed to go to L2 and not L1.
And it's almost redundant because you use the if statement.
There is no else in this case.
Right.
But there's only the if.
Almost redundant because you're already using an if statement.
Correct. But this if statement only has one then statement. It doesn't have an else statement. Is that okay? There's no else corresponding to this particular if. So that means the second version of the code is not structured. Now, how many people remember what is the title of cisp310?
Introduction to structured programming.
Exactly. Introduction to structured programming. So how come tech is undoing or trying to undo everything that you learned in cisp360? Because in assembly language, there's no structure. So if you want to translate your program, your C code into assembly code, you have to get rid of quote unquote the structure. Now, I would also strongly argue that this is actually not unstructured. This is still structured because if block one has its own conditional statement, it'll be expanded, independently. So you can maintain the structure of a program as far as the control structure is concerned. It just doesn't look structured anymore. Okay? Yep.
Could you go through the first two lines with translates to, and then if not C, go to L1. And then after that, is that
Block one. This is BLK1, which is the same block one that you see here. And this is block two, which is the same as block two here. So the block one and block two can be no statement. It can be, any number of statements.
and that's being triggered by the if statement at the top, or is that just a separate line of
Well, what do you think? This is plain C code. So what is the syntax of a conditional statement in C? Okay, let's find out. Okay, I'm not asking that question, to imply anything. I'm asking the question to get you guys to start to think about what is the actual syntax of a conditional statement in C. So we'll say C conditional statement syntax, and I'm pretty sure this will find something. Okay, and we'll find something that this may be too much. Okay. All right. Maybe I'll just use an example of my own to illustrate this. But this is important because I think a lot of people may think they understand C syntax, but in reality, they actually do not. Okay, so there we go. All right, so to describe the C syntax, it has an if, okay, as a conditional statement. And then I'm going to use this to represent that it's a token. In other words, everything else is verbatim. But if I use the angle brackets, it's a token, which means it is to be expanded to something else. So in this case, the condition is supposed to be something else. I'm just using angle bracket C to say that this is just a placeholder for something else. Okay. Now C does not take a the keyword then, okay? So it is immediately followed by a then statement. The then statement is a single statement, okay? And I'll illustrate what I mean by that later on. Do you guys still remember this symbol when we talked about regular expression? It means, oh, it's not this one. It's the other one that means optional. So I have to debate, to see which one we should use in this case. Okay, so in using that particular syntax, we have to use curly brace, and then we indicate that, curly brace, and then the word else, and then we have the else statement, and then end curly brace, and then we have to specify this is optional, which means it can occur 0 or 1 time. Does anyone remember, how we specify 0 or 1 time? I actually do remember. I want to see if you guys remember. Okay. It's a question mark. / question mark is optional. Okay, so this is the kind of more concise version of looking at the C syntax. The curly brace here is not actual curly brace that you put into C. I know it looks confusing because C also uses curly braces. But the curly brace is only here to group the word else with an else statement. Okay? So this is the actual syntax in C and C++ for conditional statements. So what I'll do is I'm going to show you some examples and see if you guys can find out what is going to happen with these conditions. So we'll just say if x is less than y, this is actual code, okay? So pretend that there are two variables, x and y, okay? And they can be compared. And then we have, x gets y here. And if this is my entire conditional statement, and the next thing, is while, blah, 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 okay? It doesn't even matter what that is, after this, but I'm just pretending this is the fragment of code that we are analyzing, okay? Do we understand what this code is going to do? Yeah, I think we do, right? So if x is in fact less than y, then x will become y, right? But we'll do the loop regardless because the while loop is after the conditional statement. Does that make sense? Are we good? Okay. So now I will give you a slightly different variation of this and say, what if I say y itself gets 10? So syntactically speaking, or if you look at the indentation, it would seem to suggest that y equals 10 is also part of the then statement. But that is not true. Because the conditional statement in C and C++ only takes one single statement after the condition. So that means y equals 10 is technically after the conditional statement. Y equals 10 executes all the time, regardless of whether x is less than y. Is that okay? Do we get this part? Okay. So what if I want both of these statements that are indented to execute when the condition x is less than y is true? The only way to do that, well, not the only way, but one way to do it is to use curly braces. Because what curly braces do in C and C++ is it is called a block statement. It is a container, kind of like a folder. So the rule of the conditional statement is you have the word if, you have open paren, you have some kind of condition in between, and then you have the close parenthesis. And then what follows is important. You have one single statement to specify what you want to do when the condition is true. You only got one thing you can specify. So if we use the analogy of a file system, you have one thing. Okay, now that one thing can be a file on its own, can also be a folder. So if you use a single file, then that is it. Okay, that file is the only thing that you do if the condition is true. If you have multiple things that you want to do, then you have to use a folder to contain those multiple things that you're trying to do. There was a question back here. No? Are we good? Okay. So now the question is, all right, so if that is the case, okay, we'll go back to the first version without this line here. And we say else y equals x, okay? I have no idea what this code is going to do, but this is just an example. So do we understand this code, what it is going to do? Yeah, I think so. If x is in fact less than y, then x becomes y. If x is not less than y, which means if x is greater than or equal to y, then y becomes x. Right? Okay. So let's go ahead and reintroduce the other line that we saw earlier. So what if I say y gets 10 over here? What do you think is going to happen in this case? Does anyone want to give it a try? Go ahead.
Will it be an error?
Yes. What kind of an error is it?
Yeah.
Exactly. Now that is good analysis. So in this case, by the time the compiler sees y equals 10, by the time it sees the y of y equals 10, it says, okay, we are done with this conditional statement. Because the only thing that can happen in place of this y is else. If it does not see else, it means the conditional statement is concluded. Now, the syntax error does not occur when it says y equals 10. Because the compiler would just say y equals 10 is after the conditional statement. Not a problem, okay? The problem happens when it sees the word else. because this else, assuming this code is at the root level of a function definition, then this else has no if to correspond to. And then it'll just go like, nope, can't do this. Okay? That is the nature of C and C++. And that is also why when I specify the template of code to do the conversion, let me go back to my own notes here. And that's why I use curly braces here, because block 1 is not necessarily just one statement in C. It can be a group of statements in C. It can be a sequence of statements in C. So I have to emphasize to use the curly braces to make sure that the conditional statement treats this entire block as one single statement, as a block statement. So did I answer the question earlier?
Yeah.
Okay, great. This is also, there's a difference between, how people teach cisp310. Some professors start with the syntax, like what I just did, and some other would start with actual sample code to use, basically teach by examples. If they only teach by examples, then the actual syntax of C or the significance of the actual syntax of C will be lost. Okay, so getting back to here, are we still okay, looking at the equivalence? So, the original question is about this line. Let me highlight that first. Okay, so the original question is about this line here, and also the line right after. Okay, what does that mean? Well, this means go to L1 is the then statement associated with this conditional statement. And that is the only thing that is associated with the conditional statement. Because guess what? You only get one statement that you can specify in a conditional statement. And the go to L1 is that statement. Is that okay? Which also means block 1 is not associated with the conditional statement at all. If the conditional statement does not fire, in other words, if not C is false, it falls through to the block 1. Is that okay? All right. But why do we want to break a program down to something like this? If you just look at the first line that is highlighted, that's our conditional branch. When we have JLI, JSI, JOI, JCI, and so on, that is what we are trying to get to. Is if and only if a flag is a 1 branch, go to somewhere else. Is that okay? All right. So are we still doing okay so far in terms of looking at both pieces of code and understand that these two are functionally equivalent? This block of code versus this chunk of code. Are we good there? Okay, very good. So the second one is basically just a simplified version where there's no else statement. So if you do not specify an else statement in the structured code, then the flattened code looks a little bit simpler. And that's about it. Are we good so far? Because in this case, it is the same thing as looking at block 2 being entirely empty. If block 2 is empty, which means you don't have an else statement, this block 2 here is also empty, which basically means, you just go to L2 here, and, there's a go to L1, which we retain, but this go to L2 is redundant because L2 and L1 are actually the same without block 2 actually being there. Is that okay? So it's an optimization. The next one has to do with the pre-checking loop. I know most people want to call this a while loop, but I just want to call that a pre-checking loop, where the condition is checked before you perform the body of the loop. So if this is the original code, okay, which looks really nice, simple, structured, that gets translated into something like this. So are there any questions? Are there any questions about, how that works? Do you see how the condition is inverted or, flipped or negated? Because instead of looking for the condition to stay in the loop, it is actually easier to look for the not or the negated of that condition and say, when do we get out of the loop? And then we label L2, that is outside of the loop. We perform block 1 if the condition is still true, because if the condition is if condition C is true, not C is going to be false. If not C is false, we are not going to label L2. Then we fall through to block 1, which is the same as block 1 over here. We perform the body of the loop. After we perform the body of the loop, we have an unconditional go to back to label L1, because we have to reevaluate whether the condition to get out is true or not. Yes?
Did you say that if C is false, then we are going to L2 or no?
If not C.
Okay,
If not C is false, then we are not going to L2. That means we go to the body of the loop. But if we perform the block of code in the body of the loop, we also have to remember to go back to the label L1, basically to ask the question again, can we get out now? I probably spoke if not C is false.
I'm
We
sure
can.
you did. I probably missed it.
I cannot remember either. We can go back to the video and check, but what I meant to say is if not C is false, then we are not going to exit the loop, and instead we will go to the body of the loop and perform whatever we need to do per iteration. So are we good with this chunk of code? Yep, go ahead.
Does the code speed increase if you write it this way?
You mean when you compile both versions of C?
Yeah.
No, it does not increase. It might even decrease, okay? Because what C does, or what the C compiler does, is internally it will translate this code to something that looks like this, but it is in an intermediate format. So we don't get to see that. But that's what a compiler would do, is it would turn structured code into basically unstructured code, because eventually the compiler has to spew out opcode for a particular processor, and no opcode of any processor is quote structured. So, but I said it might even make it slower, because if you specify your code like this, which is flattened, the compiler can no longer use its own tricks to try to optimize. So you might basically just you might hinder the optimization capability of a compiler if you pre-translate structured code into flattened code. But in this class, we are not too concerned about optimization, so we'll just go ahead and do this step by step. Any other questions about a pre-checking loop and how that is translated into, how it is flattened, basically? Are we good? Okay. Moving on to a post-checking loop. It's a do loop. So this particular loop using a do while translates to something that's actually simpler. We just have an L1 to mark the beginning of the loop. We have block 1, which is the same as the body of the loop. It is performed first. And then if condition C is true, we go to L1 because we have to go back and perform another iteration if C is true after block 1. So do we have any questions about section 3? Section 3.1 for conditional statement, 3.2 for pre-checking loops, and then 3.3 for post-checking loops. Question? Yes? A for loop? Okay, so a for loop is basically a while loop. So if I were to say, okay, while for, okay, this is the initialization part. I'm just going to use this token to represent the initialization. This is the condition, which is what you check, and this is the post operation per iteration, right? And then usually you have a single statement after that. So that is the construct or the syntax of a for loop in C and C++ and many other languages as well. So what this translates to is I is done first before the loop. It is the initialization. Then you have basically an implicit while loop using C as the condition. And then in the body of the loop, you will have statement performed first, and then you will have the post operation performed right before the end of that iteration. So a for loop is really just a fancy way or a better way to represent a loop, a while loop, because you're clearly putting, you can put all the initialization code into here, into the I token, and then the condition is the same, which is the C token. And then you can also specify the post operation related to the condition in the P token. So the idea is anything that you use or is related to the condition, the initialization and the post operation, they now appear to be in the same place, and that makes the code easier to look at and easier to analyze. So ideally speaking, you can put anything into the initialization, whether it has something to do with a loop or not. Okay, and yes, you can even absorb a lot of the statement itself into the P token. Okay, because nonetheless, they're both part of the body of the loop. But what the intention was is anything that you use in the condition, whether it has to do with the initialization of the variables involved, or something else, those need to belong together. So it's easier for you to relate. Oh, this variable is used in the condition, and it is initialized like that. Okay. If you have any post operation related to the variables in the condition, you should also put it into the post operation portion. So when you read the for loop, it is easy for you to see, oh, okay, I is the indexing variable. I has to be less than blah, blah, blah to stay in the loop. But after each iteration of the loop, I is incremented. So plus plus I goes into the P token. Is that okay? But that's a long answer to the original question, which is, what about for loop? For loop is really just a fancy case of a while loop. Now switches, okay, because switch statements is not mentioned in here. Switch statements can be seen in some cases as a if then else or a multi-level if then else, because you're basically checking whether a particular value, whether a variable has a particular value. If so, it goes into that particular case. But the effect of falling through a case to another case in a switch statement cannot be easily emulated by a if then else structure. I do not really like that portion, of a switch statement of automatically falling through if you do not say break at the end of a case. But that's basically what the language standard specifies. Are we good so far? All right. So getting back to the notes, and that's it. Section 3 is about control structures in C and C++. So we mentioned for loop, which is really just a more concise version of a while loop. I mentioned switch statements. We are not going to touch switch statements in this particular class. So that's it. That's all. Those are all the control structure statements that we have to handle. But the complexity of translating into assembly code is not really that much about the control structure. Sometimes, or most of the time, it has to do with what is the condition that we are specifying here. Because that little c, okay, can be the placeholder of a gigantic Boolean operation that has multiple levels of and, or, nots, and whatnot, right? So how do we deal with the cases when C itself is a complex operation? That's what section 4 is for. Section 4 would look at the Boolean operators and say, well, if the original if goto looks like this, then we can get rid of the negation symbol by making the control structure a little bit more complicated. So do we agree that these two blocks of code are functionally equivalent? Okay. Now, the second version is very clumsy. It has to add one label definition, one additional goto, just to get rid of the negation. So if possible, we would want to avoid having to do this, because a lot of times the negation can be dealt with using various Boolean transformations. Yes?
Also, just to make the top one more like the transform, underneath the if statement, right underneath, would you put go to L2?
Go to L2.
So like transforms, it's like if C, go to L2.
Mm-hmm. And L2 is what we call a continuation label. It just continues with whatever is after the original statement. Is that
Not really, but I'll ask you later.
Sorry?
I said not really, but I can just ask you in lab.
Oh, okay, sure. Yep, go ahead.
Where is L1? It says go.
L1 can be wherever. I don't really care what L1, where L1 is defined, because this is the original statement. I just want to get rid of the negation.
Oh, okay.
So wherever L1 is, I'm going to L1 when C is false. Because if C is false, I'm not going to label L2, which means I'm going to label L1. But if C is true, then I am going to label L2, and L2 is here. Whatever is after L2 is whatever is after the original statement. So I'm just continuing to do whatever I needed to do when C is true.
I know you said there's no structure, but will just because your example is right here.
Mhm.
Will your L1 always be before L2? Like the
No.
placement? No. Okay.
No, they're just placeholders.
Oh, just placement.
They're just, L1 is saying this is where I wanted to go originally, and L2 is a continuation label.
All right.
Okay. Any other questions? No other questions? Yep, go ahead.
Continuation label as in you just basically are skipping over the go to L1 line?
Yes.
Okay, yeah.
Yep. So L2, the whole purpose of L2 is really just to get around go to L1. But the idea is we only want to have a single go to as the then statement of a conditional statement. That is the restriction that we have to play by, because that eventually will translate to conditional branches like J something I. So are we good with 4.1, how to get rid of negation? So as I said a little bit earlier, we can usually get rid of a negation by transforming C itself. So instead of complicating the logic like this, there are other ways to move the negation inner and inner, so that we don't have to go through this kind of transformation. I'll show you, an example later on. The second one is an OR. Okay, so if you look at section 4.2, it's an OR, which basically says if the original condition is C or D. Okay, now once again, C itself can be a complex expression. D itself can also be another complex expression. So the OR is basically saying this is the last operator of the entire expression in the condition. Is that okay? Are we doing okay so far with this? The OR is the last operator to apply in the condition of the original conditional statement. You had a question? Yeah, go ahead.
So when we're defining L1 or L2 or the labels, once we give a definition to the label, is that the only definition that's applied, or can it change?
Oh, you cannot just reuse the same L1 and L2. So the L1 and L2 are really just there as a placeholder. So whenever you see the original code has L1, but the transform code has L2, that means make a new label to handle that. Yep.
In the condition, actually in section 3, when we went from C control structures to assembly-ish kind of things, does that mean we also have to further transform every not C into like one of these?
Well, not necessarily. So we'll deal with negation is a little bit special because we can apply De Morgan's law to move the negation, into the and or.
Oh, if C is a complex expression or something?
Yes. So all the expressions involved in the condition of the original conditional statement can be complex. So the C of section 4.1 can be a conjunction, can be a disjunction as well. It can also be just a comparison. Is that okay?
So we kind of just use like Boolean algebra to
Yes.
answer good.
So we use certain tricks in Boolean algebra so that we can move the negation around to avoid having to use that ugly trick to add more go-tos and label definitions. All right, but looking at section 4.2, are we convinced that this code here, if C or D go to label L1, can transform to if C go to label L1, if D go to label L1? And this actually also preserves the short-circuited evaluation of Boolean expression in C and C++. Did you guys learn about short-circuited, or otherwise known as lazy, Boolean expression evaluation in C and C++ in 360? Another facepalm moment. Okay, so lazy evaluation means in a disjunction, if the first condition is true, you don't bother to evaluate the second or the right-hand side. Okay, that's called either lazy or short-circuited evaluation. Now, it is important, okay? That is actually a very, very important concept because there are certain loops that count on short-circuited evaluation, okay? It will work perfectly when the programming language makes use of short-circuited evaluation, and the code will break if the language does not support short-circuited evaluation. So you kind of have to, this is important, okay? So I'm kind of glad that we get to see disjunction this way because this code, what it transformed to, quite clearly states that if C is true, we are not going to bother with D because we're already off to label L1. Wherever label L1 is, it can be before, it can be after, it can be somewhere else. It would just have branch already if C is true. We don't even bother to evaluate D. Okay, are we good so far? Okay, so we'll move on to section 4.3, which is about conjunctions or ands. Okay, so and is a little bit less symmetric compared to or, because if the original condition is C and D, then it translates to this code here, which says if C is false, don't bother. We'll just go to the continuation label. That is once again short-circuited. Because in the conjunction, if the left-hand side is false already, don't even bother with the right-hand side. Because false and whatever is false. Is that okay? So this is true as well in all C compilers. In fact, most programming languages today make use of short-circuited evaluation when it comes to Boolean expressions. Is that okay so far? Are we good? So now, if C is false, we go straight to label L2, which is a continuation label, to continue with whatever is after the original conditional statement. What if C is true? Well, if C is true, then not C is false, which means we are not going to L2 right away. Then what do? Well, we go to the next statement. The next conditional statement says if D go to L1. But the fact that you're on the second conditional statement means C is already true. If D is also true, then we go to L1, which is what the original code intended. So are we good so far with section 4.3? Are we good? Yes? Excellent. We are done. You are now officially a compiler. As far as conditions and control structures are concerned, you have known every single trick that you need to know to translate C code into assembly code, with the only exception of switch statements, which I said earlier that I don't like to begin with. Is that okay? All right, but there are other things that I need to talk about. It has to do with reductions that can be done in a way that can simplify your code a lot. So we can look at this code here, okay? The negation of x is greater than or equal to y translates to x is less than y, right? So in this case, we are applying Boolean algebra to get rid of, so that we don't have to do some control structure expansion to get rid of that negation. Is that okay? The second line is also the use of a reduction technique, because if the original statement is if x is less than y or x is greater than y, then we are really looking into whether x is different from y. Is that okay? So we can actually combine, we can get rid of the or because we understand the meaning of the two comparisons and the or, and we can say, oh, that really just means if x does not equal to y. Are we good with this so far? Okay. So there are other translations too. I did not mention it in the slides, so I probably should add it. Okay. So the other ones, one makes use of, they're mostly based on De Morgan's law. So De Morgan's law says, if you have not A, C, and D, okay, this is equivalent to the negation of C or the negation of D. Okay, but why is this helping us? Because it looks like we're making things even worse, right? Because originally we only had a negation to deal with. Now we got two negations to deal with. Well, but remember, all of these negations can also make use of the other tricks that we have mentioned. So the idea is maybe eventually one of these negations can be quote unquote dealt with just by using a trick and turn a comparison into a different comparison. Okay, so we want to move the negation to be inner and inner and inner into a complex Boolean expression. So the other trick we can also do is also De Morgan's law, but this time it applies to OR. So if you have C or D, and then you have a negation as the last operation, that translates to not C and not D. So once again, we are moving the negation inside so that hopefully when we perform, if C itself is complex, then we can apply De Morgan's law again. So every time you apply De Morgan's law, we're moving the negation operator to go inner and inner and inner, because eventually, most of the time, okay, it boils down to a comparison. And the negation of a comparison is very easy to deal with when it comes to, we'll just flip the direction of the comparison, or we look for different flags, okay, after the comparison. So that's why we like to apply De Morgan's law as much as possible, so that this way we don't have to go through the kind of the tricks that we do in control structure by adding more go-tos and more labels. So are we good so far with this part of the discussion? We good with this part? Okay, very good. So switching back to the notes here. So section 5 talks about comparisons. Basically, the only thing the processor, our processor, text toy processor, can deal with is to determine whether one of the 5 flags is true or not. Okay, and it will only do a conditional branch if and only if the flag is true. So what five flags are we talking about? We're talking about the C flag, which is good for unsigned comparison, making sure the minuend is less than the subtrahend. Okay, what did you just say, Tech? Refer back to the binary comparison module. Okay, we talked about that in that module. So the C flag is good for the minuend being less than the subtrahend, but using the unsigned interpretation. The next one is the Z flag, which is the zero flag. The zero flag is a 1 if and only if the result after an arithmetic operation is 0. We can check for equality because you can now compare two registers. If after the comparison of two registers, the Z flag is a 1, that means the two registers are the same. So we can confirm less than, we can confirm equal to, just natively because of the instructions that we have. The next one up is the sign flag. The sign flag by itself is not that useful because we know that in the case of an overflow situation, the sign flag cannot be trusted to indicate whether the minuend is less than the subtrahend. But there are other cases where the sign flag by itself can be useful. Your assignment or the lab for today is one of those cases. The next one up is the overflow flag. Okay, the overflow flag is almost always not very useful by itself, unless you want to catch the cases when the result after a subtraction cannot be represented using only 8 bits. Okay, so if you want to double check and make sure that we are not overflowing the representation of a signed number, the overflow flag can be very useful for that, but not usually after a comparison by itself. And then the very last flag that we talk about is the L flag. The L flag is the exclusive OR between the sign and the overflow flag. And the way we use the L flag is a 1 if and only if the minuend is less than the subtrahend, but we have to look at the values from a signed perspective. All right? So those are the flags, those are the meanings of the flags, and we talked about all of this already when we talked about binary comparison. Are we good so far with that? Yes? Okay. So what it boils down to is we have the innate ability to confirm less than. We also have the innate ability to confirm equal to. So if that is the case, what can we do to translate code? If the original comparison is x is less than y, we keep it. If the original code is x is greater than y, we translate it to y is less than x. Right? And that's a pretty easy one. If the original code is looking for x, trying to confirm x is less than or equal to y, we translate that into x is less than y or x equals to y. If the original code looks for x is greater than or equal to y, we do the same trick. We just flip the position of x and y. If the original code looks for or tries to confirm x does equal to y, so this x equals y is a comparison, which means in C code it would have been x equals y. Okay, it's not an assignment operation, but we can confirm. Oh, I see the mouse cursor is at a very bad place. Okay, so x equals y can be confirmed by the z flag, so we can just leave it as is, and then not equal to translates to the negation of x equals to. You can also look for greater than, but that's a little bit actually more work compared to just negation. So are we good so far with comparisons? How we reduce some of the comparison operators to things that we can do innately using conditional branch instructions. Are we good so far? Yes? Do you guys remember? Oh, okay, there's a question back there. Yep. Oh, you're good. Okay. Because with these glasses, I cannot focus on far objects. All I see is kind of like a fuzzy things when when things are too far away from me. Okay. So now, let's say we have this thing here. Now this looks really kind of abstract because that's the intention of this particular notation. Is R is one of the relationships. Okay, it's one of the comparison operators. In other words, R can be less than, R can be equal to. Because those are the only two things that we can confirm natively using the opcode that we have in this toy processor. Is that okay? So R is just a placeholder for either less than or equal to. So the question now is, so what do we do with something that looks like this? If X is a register and Y is also a register, that translates to something like this. Compare XY and then JR, that should be JRI, okay, that should be an I after this, L1. So this is where we translate to actual assembly code. If X is a register and Y is a register, then the original statement in C, if X is R, if X, R, Y go to label L1, it becomes compare XY, which is a single instruction, and then JRI L1. Where R can be one of three things. Can be C if we're looking for less than for unsigned values. Can be L when we are looking for less than for signed values. Can also be Z if we're just looking for equality. Are we doing okay so far with this particular slide? I'm going to go change this JR to JRI in the notes. So just give me a moment here to do that. Okay. And this one is in which module? It's module 303. Oops. There we go. And we're looking for JR space. Give it an I, line up. And it doesn't go back to where I left off. So excuse my scrolling here. There we go. Okay, so JR becomes JRI. So here's a comparison. Assuming we have the following C code, X and Y are unsigned, okay, then if X is less than Y, go to L1, becomes compare XY JCI L1. Because the flag C, or carry, otherwise known as borrow, is set and only if the minuend is less than the subtrahend from a unsigned perspective. Are we doing okay so far with this? Yes? Okay. Cool. So the next one talks about what about nesting and labels? In other words, what if you have a conditional statement inside the conditional statement? Then what do we do about the label names? Okay. Now you can always just keep using a counter and say, oh, L5 is used, the next one is going to be L6. L6 is used, the next one is going to be L7. Eventually, you will lose track of which label has been used already. And the worst thing you can do is not to refer to a label that is not defined, because the assembler will tell you that this label is not defined. The worst thing you can do is to mistakenly use a label that is already defined, but it's the wrong label. Then your program, the control structure of your program will just go to the wrong place, but it won't give you a syntax error, so to speak. The assembler would not be able to catch it. Okay? So this whole section talks about a strategy of how we can make new labels related to the control structure so that we don't have a problem with that. And it has to do with the use of basically suffixing the labels. So there's one portion that depends on the counter if they are at the same level, but at the same time, when you have nested stuff, then we have something that is nested, like this label here. So this is corresponding to the outer construct is a loop. So the loop one, is saying the ancestor of this control structure, the name of the ancestor of the control structure. The second part is what we're dealing with right now, which is a conditional statement. So we're dealing with a conditional statement inside the loop. That's the original code. This is the flattened code. So you may not like the way that I, name the labels, because it does get pretty long and tedious and whatnot. Whatever you do, come up with your own method that is systematic so that you do not accidentally step on the label incorrectly. Okay, but it's up to you. Okay, this is just the way that I would do it. Obviously, inside the compiler is a whole different story, because compilers can keep track of numbers really easily. Okay, it doesn't confuse a compiler when you have hundreds of labels and they're all L something. But in your case, because you're not actually technically a computer, understanding the context of a label can be more helpful. Is that okay? So there's an example here. Okay, Boolean operator reduction transformation. So in that case, you basically need to also make use of newer label names, because in this case, this is the original construct. So when you translate this construct into here, we are introducing a new label, which is this one here with the underscore one, and it is defined down here with the underscore one. So whatever you do, make a systematic way so that you can do it. And here is the sample code. What if your original code looks like this, assuming X, Y, Z are all in registers already? Okay, so this is the original code, and the finished product is all the way down here. And eventually it boils down to something that looks like this. I'm just not going to explain this. I'll let you guys read it, because if I try to read this section of code, I think 2/3 of the class will fall asleep. But the idea is you do it step by step. You do it one level of the control structure at a time. Is that okay? Cool. Now there are other tricks that I can tell you too. So instead of trying to translate the entire C code into assembly code and then cross your finger to hope that it works, this is the trick. Okay, so I'm backing up to a point where the code is flattened, but it is still in C code. Okay, I'm just going back up. No, it doesn't. Okay, I was doing translation into C code right away. But if you apply the techniques that I talked about, everything is still C compilable. If you just use the flattening technique that I talked about earlier. So what does that mean? You can still use code blocks or whatever favorite IDE that you want to use to debug your code. Because every single time I transform the code, it does not change the meaning of the code. So if your original code is working, so should be the transformed code. So you can actually test your code using your favorite C compiler and the IDE that you're used to until it is time where, okay, I have done every single flattening I can possibly do. Okay? At that point, then you translate it into assembly code. But up to that point, you can still use a C compiler and a debugger with a C compiler to do it. Does it make sense? Yes? Okay. What if somebody complains and say, well, C is a dying language. I think JavaScript or Python is the new thing to do. Well, do it in Python then. The technique that I just mentioned can be done in any programming language that has the construct of a label and a goto. And I'm pretty sure Python has that too, even though it is heavily frowned upon. Of course, if you do this in Python, then the indentation becomes important. So, you basically will have to get rid of all the indentation because eventually, after the entire flattening process, there should be no structure left in your code. And in Python, that translates to no indentations whatsoever, except for the if and then the goto. They have to be on two different lines, I think, in Python. So are we good so far with this particular module? More or less? Okay. So let's go ahead and work with an example, okay? Because I think if I show you how it is done using an example, you guys can start to ask questions about the process. So let me go find my. There we go. Okay, so I'm gonna start with some code here, and let's just say that we have. I'm gonna use only registers in this case. So register A is initialized to 0. Register B is also initialized to 0. And then the code looks like this. If A is less than 10, this is actually the way that I code is whenever I use an open curly brace, I end it right away, and then I go back to fill in whatever is supposed to be between the curly braces. Why do you think I do it this way? So I don't forget, and the indentation will be automatically correct, assuming your editor supports auto indenting. And this way, I don't have to later on try to figure out, okay, so how many closed curly braces do I need? Because you can miss a level of the closed curly brace, or so move the order. Well, I shouldn't say move the order, but if you do not put the closed curly braces at the right place, even if it's the correct number, the compiler does not complain, the logic may be wrong. So I always do it like this. Okay, so in here I will say if B is less than 30, okay, we'll do the following. B gets B minus 30, and then A equals A plus 1. And then after that, I say B gets B plus, I don't know, 17, okay? So this is the code that I want to translate. There's actually a particular purpose to this code. I'm not going to get into the purpose of this code here. For those of you who are interested, this is also called a frequency divider. Okay. All right, so how do I translate this code? You get to pick, okay? You can either choose to deal with the if first, or you can choose to deal with the while first. I would do the while first, okay? Because the way I like to do this is I like to do the translation from outside in. So I would start with the outermost control structure and then move my way in into the inner control structures. So I will deal with the loop first. Okay, so let me copy and paste the code because I don't want to modify the original one. So now I have version 1. Okay, so version 1 doesn't do much except all it does is to say if this is not true, go to while end. Okay, so I'm going to say while one end, even though there's only one while loop, I might as well start to label it. Okay, and that label is going to be defined here, while one end. And because of that, I don't really need the control structure here anymore. But before I get rid of those, I better say this is while one begin. And at the very end of each iteration, I have a goto that is unconditional to while one begin. So once I have done all of these steps, these two or this pair of curly braces would no longer be needed. Okay, so let me see if you guys can agree that this code is still doing what the original code is doing, except I have just flattened one level of this code. Are we convinced? Yes? No? Maybe?
It looks good to me.
Looks good? Okay. Does anyone have any questions about this? Because all I did was to apply the template that we defined earlier of how to flatten a while loop. That's all I did. Are we good so far? Except instead of using L1, L2, I choose to use labels that are more meaningful. Is that good? Okay. All right. So with this done, I'm going to move on to version 2. So version 2 is to take this code and go like, well, we still have some structure here. The way I can tell there's still some structure here is because of the use of curly braces. So I look at this and go like, the curly braces is here. Okay, so that means I have to turn this conditional statement into something that is flat and has no curly braces. So the way I do this is the same thing. If this condition is not true, let's go to the end of this conditional statement. So this basically jives with something that I said a little bit earlier. Okay, so I turn this into while one underscore if one end, which basically says this would be the end of the first conditional statement inside the first loop. Okay, now I know it is not needed. Okay, most of you do not want to make label names unnecessarily long, but if your code is complex to begin with, this can help you identify, what is this label about? Oh, this is the end of the first conditional statement inside the first loop. Okay, then you can easily go back to the original code and be able to identify where is this in the original code. Well, it's the first conditional statement of the first loop. Where is that? Okay, so once I have this goto and the label corresponding to that goto, I can now remove the curly braces. Now I'm not changing the indentation because I want to keep the indentation so that it still shows me what code is embedded into what other code. So the indentation is kept here because I'm still preserving the structure of the code from the perspective of which control structure is embedded into which other one. Okay? But I'm no longer, in terms of the programming language, it is no longer structured. Are we good so far? So, do you think this code can compile in a C compiler? Yep, it will still compile. So that means I can still test the program using all the same techniques that you have been using to debug a C program. Okay, so until this code performs exactly the same way as the original code, I'm going to fix it without worrying about assembly code whatsoever. Is that good? Okay. So I look at this and go like, well, we got a few, negations, okay? Can we deal with those negations? Okay, let's find out. So we take this code, and let me say version 3 first. So this is version 3, And version 3 says, we want to deal with all the negations. We don't like negations.
Okay.
Yeah.
I think it's gonna fall through to the b equals b plus 17.
Say that one more time.
I think we're missing a go to after the block one of the if statement. For the else.
So are you talking about here?
Yeah, because it executes b equals b minus 30 and a equals a plus 1. It's gonna just continue executing and execute the else. Unless that was not else.
There's no else. There was no else to begin with. This is the original code.
Okay.
B gets b plus 17 is after the conditional statement.
So it always executes that.
It always executes. Yep.
Okay. Sorry.
That's okay. It's always good to double check. But this is also good because it also shows us why the label names are useful, because this shows us that b gets b plus 17 is after the end of the first conditional statement of the first loop. That makes it possible for me to go back to the original code and locate where that statement is supposed to be. Right? So it's a pointer in a way to go back to the original code. All right, so we don't like the negations. So now the question is, how do we get rid of the negations? Okay, so we can get rid of this negation by turning this less than into greater than or equal to. And same way, we can get rid of this negation and turn this into greater than or equal to. Is that okay? Then somebody's going to complain and go like, but we don't like greater than or equal to either. Okay? And if you cannot remember what we want to translate greater than or equal to, then we can go back to the slide. Okay? And then we just go back and then we say, greater than or equal to. How do we get rid of those? Right here. So greater than or equal to becomes less than and then equal to, and then we flip the order at the same time. Okay, we can do that. So right here, I'm doing everything kind of in place, because they're minor changes. So we'll take this, and then we say, oh, we just want 10 to be less than a, or 10 equals to a. Okay, double equal. There you go. Does that make sense? Yes? Hopefully. Because all I did was to apply a template. I see this pattern, I turn it into that pattern. Is that okay? Okay, let me do this one more time. Okay, and we'll try to do this side by side. There we go. So we look at this and go like, okay, this is not something that I like to see. What do I transform it to? I look up the table and it says, well, x is greater than or equal to y becomes y is less than x or y equals to x. That is exactly what I'm going to do here, is to turn this into 30 is less than b or 30 equals to b. Is that okay? And then I can get rid of that. Are we good so far? More or less? But did you guys see that once I have defined the transformations, this part here, everything up to this version 3, the latest version of version 3 is really nothing more than just, oh, I see this pattern, it transforms into that. I see this pattern here, it transforms into that. I see this pattern, it transforms into that. It is very mechanical. Yes? Now, things that are mechanical may not be easy for us, but it is very easy for a computer to do. And that's exactly what a compiler does. Are we good? And even this code, as it is right now, using these kind of more elemental form of comparison, it is still C compiler. It is still C compilable. And you can still use a debugger in code blocks to debug this code. To test it, to debug it, this is still at a high level. Are we good so far? Yep.
This is just a question. Why do you have the go-to while one begin after instead of like right next to it? Is it just your preference, or?
You mean this go to here?
Yeah. Why wouldn't it just be like on the same line as b equals b plus 17?
Because b gets b plus 17 is is not part of the construct of how we end a while loop. So that's why they're on separate lines. This line here got introduced when we flattened the while loop.
Yeah.
And that's why it is on a separate line.
Oh, okay.
Now, if you say, but I want everything to be on the same line, you can actually do that. C does not care about line feed. So you can turn this entire code into one single line. The C compiler will still actually compile it. So the idea of separating things into multiple lines is only for us to see it more clearly, because the C compiler look at a line feed character as if a space character. It does not differentiate between a space and a line feed character, which is what we see when we see a new line. Okay? All right. So assuming this is still okay, the next question is, it looks like we're quite done here, except for the or. Okay, now I intentionally do not get rid of this or, because there's a reason not to get rid of this or. So now we can start to translate this code into assembly code. Okay, so we'll go ahead and make our version 4, which is basically assembly code. And this time I will do an in place. No, actually I'm not. I just lied. I'm not going to do in place. We'll do it like this. We'll comment out the C code and replace the actual C code with assembly code. Does that look right to you? A as a register gets 0 is basically what LDI does. Okay. And we'll learn there are better ways to do this, but for now, we'll do it using the most obvious way. This one can stay the same because we can define a label using exactly the same syntax in the assembler, so we'll just keep it. What about this line here? Well, this line is a little bit complex, so I'll comment out it first, and then we'll go ahead and find out how to do this. First of all, there's no compare to 10. In other words, this does not work, because compare can only work with registers. Why? How? Who tells you that? The opcode table does. The opcode table says, compare expects x and y. X has to be a register. Y has to be a register. It cannot deal with a constant, cannot deal with an immediate. So what that means is, we cannot do this. Which also means, we need a separate register, say D, load it with the constant we want to compare to, and then compare D to A like that. Okay, so whenever you need to compare to a constant, you have to move the constant into a register before you compare. Okay, now that we got to compare, what do? Well, we want to confirm a less than or a equal to. Now let's assume all the registers are unsigned. Okay, so we'll make that assumption. If all the registers are unsigned, less than is JCI, okay, to label while one end. Excuse me. One more time. Thank you. Gesundheit. Okay, and then the other one is JCI while one end. Whoa, wait, hold on a second here. There are two separate comparisons. Can we really do this, without comparing again? And the answer is yes. This is the beauty of the compare instruction. It changes all 5 flags at the same time. So there's no need for a separate compare instruction just to see whether D and A are the same. Are we doing okay so far? Now, what if you do another compare? It doesn't hurt anything. It's just not needed. Okay, cool. So that takes care of the conditional statement here. So that makes this conditional statement kind of the same thing, except we have a slightly different number, and also it compares against a different register. Same technique. Load D, which is kind of like a floating temporary register for now, okay, with 30 this time. And then we say, let's compare. Compare D, which is basically 30, with register B. And then we say JCI to label if while one underscore if one end. And then we have the same thing with JCI, while one underscore if one end, like that. So are we good so far? Yes?
Why did you use JCI and JZI? Why not bring those associated?
JCI would branch if it is less than, JZI would branch if they are the same.
Right.
So one catches the less than, the other one catches the equal to.
Is that because the compare flag, the
Yes. Yep. The compare instruction sets all 5 flags. Well, I shouldn't say set, but it affects all 5 flags. All right. So now we get to something that actually has to do with computation. What are we going to do with this? Well, what about this? We'll subtract 30 from B. Would that work? It won't work because subtraction also requires 2 registers. 30 is not a register. So we have to get 30 into a register and then we do the subtraction. But wait, 30 is already in a register, isn't it? Because in order for me to get to this point, I have to first do the comparison. When I did the comparison, 30 is already in register D, so I can just do something like that. Now, what if you say, I'm not so sure if 30 is already in register D? Well, you can do another LDI, okay? It just uses some additional space, it slows down the execution a little bit, but it doesn't hurt, okay? What about this guy here? We're adding 1 to A. That one is way easier because we do have the increment instruction to add a register, to basically add 1 to a register. Okay, so now we have 17 to deal with. This time we cannot avoid loading register D with 17. So we have to say D now has 17 as a constant, and we just say add BD, okay? And that's the entire program. So you can see the actual translation into assembly is the very, very, very last step. And you can do all the transformations to a very large extent and still be able to compile and test the program as a C program. It is only the very last step that you go like, okay, now we need to translate into assembly code. Are we good so far? Now, this particular example also illustrates one thing that is kind of important, which is how many registers do we have and how many registers do we need? Well, this time we have already used up all 4 registers. A, B, C, and D are all used. Okay? Huh? Register C is not used. So we have 1 register unused. But when you're actually compiling code, it would not be uncommon that you run out of registers really fast. So the question is, well, what if you do run out of registers? So we are not going to address that, at least not for the time being. We'll address that once we get into subroutines. Okay? Once we get into subroutines, then we'll talk about what you do when you run out of registers. Okay? So for today, we do have a new lab. The new lab actually can use some of the stuff that we talked about today. And it is due in a week, so if you cannot finish it during the lab time, it is okay. Okay? So we do have a little bit more time to finish this one. What we talk about in lecture today and also the module that I refer to is going to be helpful in today's lab. So I'm going to stop the recorder and then we'll head on over to the lab.